All right, let's take a look at today's lecture. We are continuing on in our coverage of tidy modeling with R. And so a lot of the content is coming from our textbook, Tidy Modeling with R. We're going to specifically look at chapters 6, 7, and 8, where we will fit a model and set up a workflow and engineer some features. And so we've seen a little bit of model workflows. We saw, fitting a whole bunch of models with a workflow in our last lecture video. And this will kind of get into a little bit more details regarding that. So let's go ahead and take a look. Okay. So first things first, we got to just kind of load up our packages. So here I'm getting I call library tidyverse and library tidy models. Now, a few of you have been coming to office hours, which is great, and I encourage you to continue to come to office hours if you encounter issues and things like that. One thing I'm noticing with students who are encountering issues is that perhaps your R or RStudio is out of date. And so if you are running into some problems, you might want to just go online, search for R, and download the latest version. Other things and also download the latest version of RStudio. And so, if you go to say Google, then you can just search for R. Okay, and then the first search result will be R project for statistical computing. The latest version right now, as of today's date, is version 441. And I recommend getting your latest version. So actually, I like to go to CRAN. I like to pick just, any place in the United States. And then you can, I'm on a Windows machine, so I'll download R for Windows, okay? And this will be that will download the file. And then the next place you'll go, we'll go back to Google. You'll download RStudio. This will take you to Posit. Okay, Posit is the company that makes RStudio, and then you'll download RStudio Desktop to get kind of the latest version of that as well. And then perhaps if you need to reinstall Tidyverse and Tidy Models, but this is what we have. Okay. So we'll load that up. We'll call data aims to load up our aims housing data set. And just so to avoid issues with outliers, we'll take the log of the sale price. Okay, so we modify aims by mutating sale price to be log of sale price. We'll store that back into aims to overwrite that. And then we'll do our initial split, right? So we're going to split our data into training and testing, and we will set the testing data aside for the end. So we're going to do training here. So we'll do initial split, and then we'll take aims 80% for training, the remaining 20 for testing, and we'll stratify on sale price, which will put the sale price into quartiles, and then kind of make sure you have the appropriate amount from each quartile there. Okay, so that's kind of getting our things there. If we take a glimpse at our data, this is kind of like structure, but this is the, I guess, tidyverse version of it. We can see, some of the different columns. There's 74 columns, and we see, different, some of the different values here. Okay. So just continuing to look at all of these different variable names. We have these are the 74 different variables, and so we see how many full bathrooms and half bathrooms and how many bedrooms above ground, kitchens above ground. Most places just have one, but some have more than one. Total rooms, etc., etc. And then as also the sale price, latitude, longitude, things like that. Okay, the first thing we want to talk about is recipes. Okay, recipes is how the Tidy Models framework handles pre-processing. Pre-processing is basically everything you need to do to set up the data and before you do the actual fitting. Okay, so this includes things like transforming any of the variables, so doing any kind of log transform, or we'll see like spline transformations and things like that. Any kind of scaling or normalizing of the data, so if you've got really big numbers or something and you want to kind of normalize them so they have mean 0 and standard deviation 1, or scale them to go on a scale from 0 to 1 or something, that's part of a pre-processing step. If you have categorical variables, then you almost certainly have to pre-process them, because pretty much all of our machine learning algorithms and statistical tools have to deal with numbers, and so you have to kind of convert your categorical variables into numbers, either into 0, 1 dummy variables or something like that. Also, if you have a numeric variable and you want to kind of create bins out of them to create like subcategories and things like that, that would also be a pre-processing step. Sometimes you have missing values and you want to impute some missing values, and so you could fill those missing values in with a mean or a nearest neighbor. There's different tools available, and so there's a whole bunch of different things you can do. You can go to the website, and this includes a whole bunch of the different kinds of steps that you can do, right? So beyond, so you have step functions for imputation, step functions for individual transformations, so basis spline functions, log transformations, things like that. Discretization, and we'll kind of take numeric variables and make discrete, make a continuous variable discrete, or cut is probably a little bit more familiar, where basically you're going to take ranges and set them up that way. Okay, so you're basically binning them into different groups. For example, income, you might say like makes less than 30,000 a year, between 30 and 65,000, between 65 and 100, 100 and 150,000, over 150,000, or something like that, rather than taking the actual, because one person might make, $64,862, and somebody makes, $61,017 or something, rather than having to deal with every single number directly, you just kind of bin them accordingly, right? Dummy variables and different kinds of encodings, a whole bunch of these different things, including if you're dealing with dates, it can calculate holidays and stuff like that, dealing with all kinds of stuff here. So lots of different functions and transformations and things are available within the recipes package, as far as the kinds of pre-processing steps that are available, right? So, this feels like basically everything I introduce in Tidy Models. You might wonder, like, why do we have to learn a whole new system to do something that I could already do, right? Like applying log to a variable, not that hard. Why do I have to do this? Okay, so I wrote, traditionally pre-processing was done manually and directly to the data. And you might even be able to save it as a script or something. But with multiple data sets, pre-processing could end up becoming this really kind of cumbersome thing. So for example, let's say you wanted to scale the data. So you end up with mean 0, standard deviation 1, okay? And remember, we split the data into training and testing, okay? So, for example, in the training data, you could end up having, when you want to scale this column of values, that column might have a standard deviation of 13.5, okay? But then when you go over to the testing data, the test data, because of randomness and whatever, maybe that same column in the test data has a standard deviation of 14.0, okay? So if you wrote your script and just said, hey, take the column, current column, and divide by the standard deviation of the column, then the training data and the test data would end up having different scaling operations, right? One is going to get divided by 13.5. The other is going to get divided by 14.0. So in order to kind of consistently scale the data between the training data and the testing data, what you have to do is you have to say, well, for this column, the training data, the value I divided by was 13.5. And so when I go to the testing data, I have to divide by 13.5. Okay? And then probably you're going to have to deal with more than one column. So you have to keep track of, basically all of the columns and, the scaling information for all of the columns so that you can apply it consistently to the test data. Okay? Otherwise, things are going to get messed up. So that would be a good reason for why you'd want some kind of automated process, because having to keep track of every single variable and what values you used for some kind of transformation function like a scaling function is going to be important so that it gets consistently applied to the testing data as well. So same things with like imputing missing values. If you just say, hey, let's impute the mean. Anytime we see a missing value, let's put in the mean of the column. In the training data, the mean of the column might be like 7.6. And so you'd fill in 7.6 for all of your missing values. But then again, on the testing data, the mean of the column in the testing data might be something else. And you don't want to use a different value. You want to make sure you still use 7.6. So the recipes package, what that's going to do is it's going to keep track of all of the steps that it's done, save them away, and then you put it into a workflow and you say, hey, I want to apply this recipe to our test data, and it will use all of the values that it's stored. So it really kind of ensures that things are done consistently. So within the package recipes, there's a few kind of key functions that we use to create and employ a recipe. So first, the first function is recipe, and this defines the recipe. And we define the recipe, we put in all of the kind of necessary steps as far as the pre-processing thing goes. So that's going to be the recipe. We often start the recipe with a formula, okay? But you don't have to. Another valid way of creating a recipe is to create like a list of variables that are going to be used, okay? And then the other part of the recipe is then you add different kinds of pre-processing steps to your recipe. You're going to say for this variable, do a transformation. For this variable, do a scaling operation or something, okay? So you come up with a recipe, and then you apply the recipe to the training data, and that's called prep, okay? So prep is the function, takes the recipe, and it says, all right, you want me to scale this variable so it has mean 0 and standard deviation 1. So when I do the training data, what I need to do is I need to subtract off 7.6 from all the values and divide everything by 13.4, okay? So when it does that, that's how it's going to prep the data, okay? And it keeps track of those numbers. And then when you want to apply it to, say, the testing data, you call bake, okay? Bake is the function that takes a recipe, applies it to a new data set. So kind of your most common scenario is called bake. If you look at older documentation for tidy models, you might see something called juice. Is the same kind of idea. They're really kind of leaning into this cooking analogy. And so I'll show you how to use prep, and I'll show you how to use bake. Later on, what we're going to do is we're going to just throw a recipe into a workflow, and then when you use a workflow, it automatically does the prep and bake steps for you, which is really nice. Okay, so we can create an initial recipe with a formula, and the formula basically use it with that tilde, sets up and says, this is the response variable. These are the variables that we're going to use for predictors, okay? So here we're going to say, I want to predict sale price based on gross living area, basically the square footage of the house, the year that the house was built, okay, and then the bedrooms above ground, okay, and these are all numeric. Sale price has already been log transformed, so we'll use these variables here, okay, and we're going to create an object. And we're going to call that Ames recipe. So we established the recipe here by just kind of putting in a formula with the variables that we're going to use, and then we specify the data comes from the Ames training data. Okay, so this is going to be applied to our training data. And so right now, if you asked what is the Ames recipe object, what it gets output says it's a recipe. The input, these are the inputs. There are 3 predictor variables and 1 outcome variable. Okay, 1 outcome variable being sale price, and these are 3 predictors. Okay, and what we might want to do is we want to add some steps, transformation steps. So here we take the recipe, and then we'll add, we'll use the pipe to add steps to the recipe object, and then we'll save all of that back into Ames recipe to kind of update it. Right? So the first step that we're going to add is we're going to scale gross living area. Okay? So what scale will do is it's going to take all of the values, divide it by a constant, and so the standard deviation of after scaling the data, standard deviation is going to be equal to 1. Okay? Scaling doesn't recenter the data, so but it's going to kind of scale everything so that the standard deviation is 1. And it will keep track of what number it used so that when you apply it to the test data, it applies the same transformation. Okay. Step normalize does the similar kind of thing, except it turns everything into z-scores, so it subtracts off the mean and divides by the standard deviation there. Okay. So now when we ask, hey, what is the recipe so far? It says, okay, these are the inputs and these are the operations. We're going to scale gross living area, and then we're going to center and scale. That's normalize for year built. So year built will have a mean of 0 and standard deviation of 1 after we do that. Okay, and then we prep the recipe. Okay, so this is just kind of the steps, but we haven't actually applied it to the data or anything like that. Okay, so we apply the recipe to the training data with the function prep, and we will also save the results of the trained recipe to this object called trained recipe. So I take Ames recipe, and now I call prep on Ames recipe. So here I piped it into prep. I could also just call prep parentheses Ames recipe. And then the result is going to be a trained recipe. So you can see before it was trained, it just has inputs and operations. Now it has inputs, training information, and operations. So inputs, same, outcome 1 variable, predictor 3 variables. Training information, it says training data contains 2,342 data points and no incomplete rows, at least for the variables that we selected. This represents a recipe after it looked at our training data, and it says scaling for gross living area, and it says it's trained, meaning it has figured out what value it needs to divide everything by. Centering and scaling, it says trained, and it says it has figured out what value it needs to do to kind of center the data and scale it. So all of that information is stored. These are some additional options. One is you can put in log the changes. True will tell you if any kind of columns are being added or removed from the data. Okay, so if you create dummy variables, then that will add columns. Okay, verbose will basically produce some output on the screen so you can see what's going on for each of these kinds of steps. Okay. If you want to see the data after you've done the pre-processing, you can do so with bake. Okay. Typically, you wait to use bake to apply the trained recipe to the new data, like the test data. Okay. And normally, you don't actually care to see the training data after the pre-processing. You would just go ahead and you would just tell Tidy Models fit the model to the pre-processed data. Okay. But sometimes you want to kind of see what the training data looks like after you use after you did the pre-processing stuff. And if you want to do that, you call bake. Okay. And here you specify new data equals null. All right. And by saying new data is nothing, it's going to say, all right, you want to see it for the data that it was trained upon. So you do trained recipe, bake, new data equals null, and this will be our pre-processed training data. And so here, I can show you that when we look at the pre-processed training data and we look at those specific variables, indeed, its mean and stuff will be adjusted, right? So if I go all the way back to the beginning, okay, so if we look for gross living area, its original values were things like 882, 864, 1092, and then I forgot what the other variables were, but you can see after I've trained it, okay, it's been scaled down, okay, and so we have 1.76, 1.725, 2.18. And so if I say, hey, select gross living area, pull that column and calculate the standard deviation, we can see the standard deviation of the column is now 1. Okay, but it was just a scaling operation, it didn't center it. So if we asked, hey, what's the mean is not 0. Okay, when we do year built, okay, year built in the original data, where did it go? Year built, 1970, 1971, 1977, 1975, things like that, okay? Year built is now we have values like negative 0.44, negative 0.0117, things like that. And so this one was a center and scale. And so when I ask for the standard deviation, I get standard deviation 1. When I ask for the mean, I get, R's version of 0. It's not exactly 0, but it's on the order of 10 to the minus 15, pretty much a mean of 0. So we can see that, yes, we applied it to the training data. Those pre-processing steps were done, and basically it has correctly scaled the data and correctly centered and scaled the data. So, sometimes I think sometimes when you run a recipe, it's natural, like, did it actually work? Just because the things that you see on the screen, you just see stuff like training information, it's been trained, and you just like hope it was correct. I think, it's reasonable to be a little bit skeptical. It's reasonable to want to kind of see for your own eyes that, yes, indeed, the mean is now 0 and the standard deviation is 1. Or at least here, in this case, the standard deviation is 1. And so here, this is how you would do it. If you want to see what the data looks like after you applied the recipe to the training data, this is how you go about doing it. All right, and I actually recommend doing something like that, especially in the beginning, if you're not quite sure if you're doing things correctly, and you just kind of want to make sure, yeah, did I scale it correctly? Did I indeed get a mean of 0 and things like that? Okay, now if we say, hey, let's take that recipe and I want to apply it to the test data, I take the same trained recipe and now I bake it and I call new data equals Ames test. Okay, so now I apply it to the test data, and now I can take my processed test data and fit whatever model we have to it. Okay, so here when I look at the test data, I can say, hey, what is the standard deviation after applying the scaling operation? Okay, and so what we see is that the standard deviation of this thing is not exactly 1. Okay, because again, it's taking the whatever scaling operation it applied in the training data, like let's say we divided by, some number, it uses that same operation to the testing data. So yeah, we don't expect it to be exactly 1. Okay, it comes out to be close because the standard deviation of the training data is kind of similar to the standard deviation in the testing data, but they're not exactly the same. So we don't expect this to end up being exactly 1. And this is, I would say, this is the big reason why recipes are important, because if you just naively said, hey, I just need to scale this so the standard deviation is 1, and then I just need to scale my testing data so the standard deviation is 1, you're going to get a different operation is going to be applied. Okay, and then so the model that was trained on the training data or fit to the training data is not going to be as high performing on the testing data where different operations were performed. Okay, similarly, when we look at year built, the standard deviation is not exactly 1. It's a little bit different, 0.975, and the mean pretty close to 0, but not as close to 0 as it used to be. Okay, so in the textbook, they continue to build up the recipe, and the variables they use, we have neighborhood, which is a categorical variable, okay, or a nominal variable. So as far as categorical variables, you have nominal and you have ordinal. So nominal is just names. There's no natural ordering. And ordinal categorical variables are ordered. So things like small, medium, large, extra large. There's a natural ordering to these categories. Okay, never, rarely, sometimes, frequently, always. Okay, there's a natural ordering to those. Categories there. Okay, so that would be an ordinal variable, but what neighborhood you're in, that's nominal. There's not like a natural ordering there. Okay, gross living area, we've seen that was numeric. Year built is numeric. Building type, whether it's a single family home or a condo or a duplex or something, that's going to be categorical, and that's nominal as well. Okay, so we start off with our recipe. This will be our simple Ames recipe. And we're going to say, hey, we want to predict sale price, which is already log 10. Okay, we did that in the very beginning. We're going to put a neighborhood. Tidy models will recognize that this is a categorical variable or a nominal variable. We have gross living area, year built, and then we add building type. Tidy models will also recognize that this is a nominal thing. Okay. Here we're going to apply a log transformation to gross living area. So we'll do step log, gross living area base 10, and then we'll make dummy variables out of our nominal predictors. Okay, dummy variables are basically going to be 1s and 0s. So if you're in a certain neighborhood, you get a 1, or if you're not, you're going to do that. So these are the operations: log transformation, gross living area, dummy variables from all nominal predictors. And you can just kind of specify all nominal predictors using this function, all nominal predictors. This is a selector function, and it will select the appropriate variables. Okay, so we will train this. Okay, and here I'm going to write down log changes true and verbose true. Okay, so we're going to take our simple Ames recipe, we will prep it to the training data, and then I'm going to call this trained recipe. Right, and so it says, operation number 1, step log to the training data. So it's applying the log transformation to gross living area, and it says, hey, the result, same number of columns. Okay. All right, step number 2, we're going to apply, create dummy variables from all nominal predictors, and it says I ended up creating 32 new variables, 32 new dummy variables. We're going to get new variable, neighborhood College Creek. Basically a 1 if it is if the neighborhood is College Creek, a 0 if it's not. Then we have another variable, neighborhood Old Town, a 1 if it's Old Town, a 0 if it's not. And it does it for all of these things. It says it created 32 new variables. And then it got rid of the original neighborhood variable and got rid of the original building type variable. So it says I added 32 variables and I removed 2 because in the training data, I forget how many neighborhoods we have, but there's a bunch, okay? And so we can kind of take a look and we can say, hey, what kind of variables did we have? So in the Ames training data, we could look at the building type, and what were the levels we had? We had 5 levels: 1 family house, 2 family, something duplex, townhouse E. I don't know what that is. Okay, and so if we just look at a few of them, we see sure these are the variables values that we have, and then basically it added four columns related to building type. Okay, dummy variables. If you have 5 categories, you only need 4 dummy variables. So the base is 1 fam. Okay, so that's going to be zeros for, so this first row with a 1 family gets a 0 for 2 fam, 0 for duplex, 0 for townhouse, 0 for townhouse E. Okay, which means if you have a 0 for all of the building types, it means it must be a 1 family. Okay, observation 2 is also 1 family. Okay, observations 3 and 4 were townhouse, so they get 1s on townhouse. Okay, observation 5 was townhouse E, so you get a 1 for townhouse E. Okay, and this way you avoid the what do you call it? Collinearity of the variables, because if you have all 5 things, I mean, sometimes you want that, okay, and that is called one-hot coding. So dummy variables, if there's 5 things, it will create 4 new columns, and the 5th one will be kind of assumed if all of the other columns are 0. Okay, and then one-hot will do you'll do it for all 5, and there will always be 1 that's a 1 and 4 zeros in each observation. Okay, so but with dummy variables, if everything's a 0, then the one that wasn't included must be a 1. Okay, so that's what we see what it did for the building type, and basically it did the exact same thing for the neighborhoods. And so for the neighborhoods, I don't know, there must have been, if it added 32, that must have 28 would be associated with neighborhoods. So there must have been 29 unique neighborhoods in the training data. I don't know. Okay. Okay, so this is basically what I said. By default, if there are C categories, step dummy will create C-1 columns. There are 5 categories for building type. If the building type is 1 fam, all the dummy columns are equal to 0. If you prefer C columns rather than C-1, you can choose the option one-hot equals true, and you have that. Okay. If the test data contains a novel value, okay, so let's say you have categories A, B, C, D, E, all right, and then in the test data it shows up with category F. What do we do? Okay, for the default behavior is it assigns a missing value. It says, well, it's not any of the other things. Okay, the reference, always check out the reference if you're not quite sure, and that's what we have. So these are the different kind of options there. Oops. Okay. All right. So that's how you set up recipes, and what you want to do is you want to put your recipe into a workflow, right? So what we'll do is we'll create part of your workflow basically needs a recipe and a model. So let's establish the model. We saw how to set up a model with Parsnip in our last lecture, where we create a linear regression model. We just specified linear regression that specifies the model, and we set the engine to LM. Okay, so this will be kind of our starting linear regression model. This will just be our LM model. We call linear regression set engine to LM. Okay, and so if we don't use a workflow, or I'm sorry, with a recipe, our process might look something kind of like this. And I didn't run this, but basically we'll take our recipe, we'll prep it to the Ames training data. We call that our trained recipe. We then train the recipe to, we ask for the pre-processed data, okay, pre-processed training data, and so I will, I get trained recipe bake, new data equals null, pre-processed train. Then we'll call LM, we'll fit the linear model. We'll do LM model fit, we give it the kind of our recipe here, sale price tilde dot or something, and we'll say use the pre-processed training data, okay? And then when it comes time to make predictions for the test data, then we take the trained recipe, we bake it on the test data, okay? This will be our pre-processed testing data, and then we say make predictions on the pre-processed testing data, and this will be kind of the fitted values. We take the fit model, and we say make predictions using the pre-processed test data, okay? And I write, if we have other models and other recipes, then having to do it kind of manually like this can make it easy to get all of these recipes mixed up, okay? So, we might forget which model and recipe combination is the best pairing and things like that. So the workflow simplifies this process, keeps the recipes and the models together. So let me just show you kind of how this works. So here with a workflow, we call workflow, and this establishes, this just defines, hey, we're creating a workflow, and then to the workflow, you add a recipe and you add a model, okay? And then you save that workflow somewhere, okay? So we're going to do workflow, add recipe. What recipe? We're going to add the simple Ames recipe. So remember, that's what we created back here, right? The simple Ames recipe takes our formula, the training data that we're using, any steps that we're applying, okay? So we say, hey, I want to add that recipe, and then we also want to add the linear model, the model to it, okay? So that's going to establish our workflow. So now when we ask, hey, what is our workflow? We have the recipe, okay, which includes, it says, hey, your preprocessor is a recipe and your model is the linear regression. And then in the preprocessor, you have two steps in the recipe. You have a log transformation and a dummy variable creation thing. And then as far as the model goes, it's a regression model, linear regression model, where the engine is LM. Okay, so exactly what we have, just has all of that information. So then what you want to do is you call workflow to your training data. You say workflow fit data equals Ames train, okay? And then that's going to be your fitted linear model workflow. And when you fit it, it's automatically going to train, like prep and bake the recipe. It's automatically going to apply the recipe to the training data, figure out all of the values it needs to do, okay? And so that's going to be in my fitted LM workflow. So Tidy Model understands the training data has to go through the preprocessor, and then the linear models fit to the resulting, transformed data. And then when you want to make predictions, then you can just take your fitted workflow and call predict on this, okay? So now that we fit the workflow to the training data, we can use it to make the predictions. We just take the the fitted workflow and call predict. And again, Tidy Models is smart enough to know that the test data has to go through the preprocessor, and it applies the appropriate values from the trained data. Okay, so it says, okay, well, this is how if you scaled it or whatever, it would apply all of those things, and does that. Okay. We do get a warning. Rank deficient fit. Okay. But anyway, we get our predictions right here. Okay, and so in our test data, we have 588 observations, and we have the results there. Okay. If you do need to kind of work with that recipe or whatever, you can extract it out. Okay, so from the workflow, with our fitted LM workflow, you can call something like extract recipe, and then you want the ones where you get the values estimated, and you want the transformations and things like that. You'll call extract recipe estimated equals true. This will return the recipe object that that's established in the workflow. Okay, and then if you want to get the model that was fit, okay, you can get the extracted. You can extract the fitted parsnip object. So if you also want to get the trained model, which you probably want to get, if you want your coefficients and your summary table with statistics and p-values and things like that, then you can take your workflow and you say extract the fitted parsnip object, right? Extract fit parsnip. And then in this case, if you want the coefficients and stuff, you call tidy on that, and it gives you back the table. And so here it gives you basically all 35 kind of predictor things. You have the intercept, you have gross living area and year built. Those are very, very, very significant, okay, as far as their p-values practically 43 standard deviations away, practically zero. Okay. And then some of these other ones, certainly certain neighborhoods, Northridge Heights seems to make a significant impact, positive impact on sale price, meaning this neighborhood's quite a bit more expensive. Neighborhood Edwards, also significant, but in the negative direction. So it seems like those, houses in that neighborhood are cheaper and things like that. So some of these, seem to have significant effects. Some neighborhoods don't really have as much of a significant effect. This one pretty much, its p-value is not significant. So some neighborhoods are, make a difference. Others do not. Okay. All right. What are some other things that can be done with recipes? So here I'm just kind of pulling this straight from the textbook, but it says, one of the most common feature engineering tasks is transforming nominal or qualitative data, factors or characters, so that they can be kind of encoded or represented numerically. And so sometimes we can alter the factor levels of a qualitative or categorical column in helpful ways prior to such a transformation. Okay, so one of these things, step unknown, this can be, we can use that to take missing values and put in a particular factor level. And then there's another thing that says if we anticipate that a new factor level might be encountered in future data, step novel can kind of allot a new level for this purpose. So this will basically, how do you handle missing values in the categorical variable? What do you put in there? If you get a new category, how are you supposed to handle that? Okay, what do you do there? And then another thing is you can create an other category. So certain categories, there just might not be very many observations. So, if you have something like 29 neighborhoods, there might be a neighborhood where you only have maybe 2 or 3 observations. And therefore, if you're going to try to estimate a coefficient based on 2 or 3 observations, it might be wildly off. So it you can't really expect super high accuracy on something like that. So it might be better to just create an other category, and then just throw every, when you have a very infrequent category represented, just kind of put it in this catch-all category of other, okay? And so here we can do this for like our neighborhoods, and we'll do add step other, okay? Add in the recipe, and we'll just say threshold 0.01. And so this basically means the bottom 1% of the neighborhoods, like neighborhoods that have less than 1%, will get kind of lumped into a new level called other. So here we'll do this, okay? Step other, neighborhood, thresholds 0.01. And so that will set that up, okay? Here, let me. So, okay, so here's kind of an example. So if you look at this, this is the count of all of the different neighborhoods. So, certain neighborhoods have lots and lots of homes, but these ones, like Landmark, Green Hills, okay, that will kind of, it says here two neighbors that have less than 5 properties in the training data, Landmark and Green Hills. And in this case, no houses at all from the Landmark neighborhood were even in the testing set, okay? So it could be problematic to have dummy variables with a single non-zero entry in the column or something. So, we'll set this, and we use other there, okay? And so there you go. All right, we can also do we can also have interaction effects when you between 2 or more predictors. And so an interaction effect happens when one of the predictors has an effect on the outcome that changes or is contingent upon one of the other predictors. So we the authors did some exploration of the Ames training set, and they found that there were some regression slopes for the gross living area that were different for the different building types. So here they created this plot, and they said, hey, how does gross living area affect sale price? And so, when you look at one single family homes, as the home gets bigger, the sale price goes up, right? Similar kind of things for townhouse. As it gets bigger, the price goes up. As it gets bigger, price goes up. But some of these things, like this 2-family complex, as it gets bigger, the price doesn't really change all that much, okay? Duplex, also, overall it goes up, but the slope on this thing is much less steep, right? So the effect of gross living area on sale price, is kind of different for 2-family, I guess condos or whatever, I don't know, and duplexes and things like that, when you have something like that, versus these other things. There seems to be a much more kind of direct relationship between gross living area and sale price. So if you want to account for something like that, you can create a recipe where it's going to establish an interaction term, okay? So to create interaction terms in R, you use the colon operator or the star operator, okay? So here we're going to say, I want an interaction between, say, the log of the gross living area and the building type. Here, if you use the star operator, log gross living area star building type, it's going to include kind of the main effects along with the interaction effect. So that's how you would set it up in base R. If you wanted to do it in a recipe, okay, you call step interact, okay? It says recipes are more explicit and sequential. They give you more control than just kind of formulas in base R. So with our recipe, we already have a dummy variable. Okay, step dummy creates the dummy variables. How do we set that up with interaction terms? Okay, so we would do step interact, and we'll put in the interaction terms, where basically the right-hand side of the tilde are the different interactions. In this case, we want interactions between gross living area and each of the building types. So we're going to say gross living area along with any variable that starts with building type. Basically, all of the nominal predictors have, they start off with building type, building underscore, type underscore, and then, one family or townhouse or something, right? Those are the different dummy variables that get established. So far, our recipe now has kind of been building up. We want to predict sale price based on neighborhood, gross living area, year built, and building type. We add a log transformation to the gross living area. We, for the neighborhood, we're going to kind of throw in neighborhoods that don't appear frequently into an other category using threshold of 1%. We're going to turn all of our neighborhoods into dummy variables, okay? And then after we've done that, we will create interaction terms, okay? So the gross living area is log transformed prior to the interaction term, okay? So that's what our recipe looks like that, okay? Another thing that, so this is regarding the interaction terms, and so you can read this. Another thing the authors have done is they said, well, if we look at latitude and sale price, there seems to be some kind of relationship, okay? The idea being, geographically, it seems a little odd, but certain parts, when a city grows or whatever, when a city, there's often like some kind of big median, like a railroad or a highway or something that kind of divides the city into different areas. And frequently, for whatever reason, oftentimes one side of the city ends up being a little bit more affluent than the other side of the city, okay? And so if you kind of believe that the city might have this geographic orientation, here we're looking at latitude. Is the north side of the city, do they contain more valuable properties than the southern part of the city or something like that? You might want to look at something like the latitude or the longitude of the house location, okay? And when we do that, this is kind of the plot between latitude and sale price. And there seems to be some sort of relationship, although a single straight line is probably not enough to really kind of summarize it. And so you might want to include, this latitude information, but you might want to refine it by using something like a natural spline. So if you try to use a single straight line, you'd probably end up with a flat line. But it does seem, looking at this plot with 20 spline terms, it does seem like in one part of the thing, there's kind of an increase in price. There's kind of an area where there's not a whole lot of housing. And then you see something kind of like this. So once you get to, say, 42.02, as you move further north, it does seem like the sale price of the house does seem to kind of increase or something like that. 42.03 maybe from there, just kind of going up. And so, having 2 spline terms probably not enough. 100 spline terms probably too much, but maybe 5 or 20 or something around there might be able to capture some information that latitude could provide without assuming that there's just a straight linear relationship. Because if you just plug in the number directly, then you will be into a linear model. Then you're assuming a linear relationship through the whole thing. That if you move up, 0.001 in latitude from here to here, it's going to have the same effect as moving 0.001 up in latitude from here to here. And so in order to kind of take into account that, maybe there's some kind of not a straight relationship, but a smoothish relationship that does have its ups and downs, you can take latitude and apply this kind of spline transformation. And that will turn the latitude numbers into basically this spline fit here. And so we can do that with a spline function, okay? Here we're going to do step natural spline. We want to do it both for latitude and longitude, and we'll have kind of the natural spline fit with 20 degrees of freedom. So here it says, when a predictor has a nonlinear relationship with the outcome, some types of predictive models can adaptively approximate this relationship during training. However, simpler is usually better. It's not uncommon to try to use a simple model such as a linear fit and add in specific nonlinear features for predictors that may need them, such as latitude and longitude. Okay, and then again, a common method for doing this is to use a spline function to represent the data. So that's what we're going to try to do. We're going to try to fit a spline thing here. And so we do that. This is what our recipe looks like. And so you can see, the recipe gets bigger and bigger and bigger, but all of these are just kind of steps that we're doing to kind of take the variables that we've currently included and just to kind of make them a little bit, more interesting. Okay, so we'll, or not more interesting, but more helpful or more useful. So we got, we take our nominal predictors and make dummy variables after we've established an other threshold. We'll add an interaction term, and then we'll take our latitude and longitude and fit natural splines to them. So if you want kind of information about the recipe itself, you can also view that in summary form, and you can just say tidy Ames recipe, and it will say, hey, these are the different steps, okay? These are the different types, it's a log step, an other step, a dummy, interact, NS. Okay, has it been trained? Not yet, okay? And then it also kind of puts in, a little ID number into the step in case you need to refer to it. And so again, how is this going to work? When you're ready to do it, you establish your model, you establish a workflow, okay? And then you add your recipe in your model, okay? So to the workflow, you add a recipe, you add a model, and then now that you have that workflow, you'll fit the workflow, you call fit, to the training data. And so that will establish your fit. Once you have your fit established, you can then apply it to the test data. And again, on Monday, we showed okay, what do you do when you have multiple workflows? You can then map this process of fitting those different workflows to, say, k-fold cross-validation, okay? And then once you apply it to k-fold cross-validation, you can do it with a whole bunch of those different models or different workflows. So you can refer back to our last lecture where we had a workflow set, and then we applied we said fit the resamples to all of those different workflows in the workflow set, and then collect the metrics to kind of evaluate how each of these things go. Okay, but this is how you would set up a recipe for pre-processing steps. You throw it into the workflow, and then now it's just a matter of fitting the workflow to the training data, and then using the workflow to make predictions, or you can use the workflow set, fit the resamples, and it will automatically do it for k-fold cross-validation, v-fold cross-validation, and then when it makes predictions, it will measure its performance. You'll collect the metrics, and then you can make comparisons that way. Okay, we'll end here for today. This just kind of introduces you to some of these concepts as far as doing pre-processing steps. Again, please do the reading. There is more detail in the reading chapters, so please do your reading. And with that, have a great rest of your week, and we'll see you next week.